I'm capturing a huge amount of data and I want to do analytics against that real time, and I have to be able to write it quickly. That could be video, it could be radio frequency. So we get involved in a lot of military applications where they're doing that kind of edge data collection. There's no way to move it to the cloud quickly. It's a huge amount of data, but they need insights into that immediately. So they'll have trained models to do local inference, and speed is also very important, and data protection.
Welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. This is Darren Pulsford, Chief Solution Architect, author, and most importantly, your host. On today's episode, real-time AI at the edge, transforming defense and mission-critical ops with Senior Director from Graid Technology, Kelley Osborne. Kelley, welcome to the show.
Hi, Darren. Thanks for having me. I appreciate the opportunity to speak to some of your followers, hopefully.
Hey, when I talked to you guys first, and I know Garrett from a long time ago, when I first heard you guys talking about your solution stack and the space that you're in, I'm like, hey, this is pretty interesting. And frankly, over the last week or so, it's become even more interesting. But before we dive into data and security and all of that, every person I have on my show is a superhero, and every superhero has a background story, an origin story. So Kelley, what's your origin story? It better be good.
Sounds great. Well, I grew up in the Southeast United States. I'm based in the Atlanta metro region here in Georgia, and I actually went into school not knowing what I was going to do and discovered computers and got a computer science major. So I started out coding, and slowly that moved and morphed into working with computer networks. And that led me to move to more companies that do more consulting, integration, resellers, that type of an environment. And I moved more and more towards the sales side of things. Because I just had fun and enjoyed speaking with people and working with people, but I still love technology. And I kind of developed a knack for being able to articulate value out of, kind of arcane technical things. So that led me to
wait. An engineer that can actually talk to people?
Sometimes.
That's unheard of.
Yeah, well, they say an extroverted engineer is one that looks at your shoes when they're talking to you, but so that kind of led me, more and more towards being, an asset to salespeople, like a pre-sales engineer. And then it was only a hop, skip, and a jump for me to move over to the dark side and become an actual salesperson. And after many years of doing that, sales management, et cetera, I've kind of found a home working in startup companies. And this is one of the ones that I've been with. I've probably done 5 or 6 startups, and all have had different outcomes, some very successful. And so that's really led me to more of a business development role. So kind of bridging the gap between marketing, technical sales, and building corporate relationships with our partners.
So it sounds like you go where the gaps are, because if I were to look at your career, you went to where no one else could be, which is actually pretty clever, right? Because you can bridge those gaps. You bridge the gap between customers and technical, and now executives and technical and customers. I mean, that's a good place to be, Kelley. So this is pretty cool.
Well, my motto's always been, if you pay me enough, I'll go away quietly. And fortunately, that hasn't had to happen. I just enjoy being passionate about what I represent. So, to me, this isn't a job; it's an avocation.
That's awesome. So hey, let's talk about some major changes over the last 3 years. I mean, the elephant in the room is generative AI, and generative AI really saved NVIDIA's keister, because Bitcoin, which saved their keister before, kind of died off, and ASICs replaced all the GPUs that people were buying. And without generative AI, NVIDIA would be nothing today. But it kind of really saved them, but it also produced a big gaping problem. and that is the sheer amount of volume of data that we have to process and that we want to process. And that's kind of where your guys' sweet spot is, right?
Sure. And, it's all about not just the volume of data, but the technology and devices that we have to use to access data. You're buying very, very expensive GPUs and creating very expensive software applications, and you don't want those sitting around not being utilized. So you need very, very fast devices to deliver that data to keep that GPU utilized, or the thousands that you may have, depending on your environment. And the other thing that's happening is, in addition to the speed increases, the density of drives has gone up and the capacity of drives. We're seeing soon on the horizon 240 terabyte flash drives from some manufacturers, and we're testing on a server right now that holds 44 drives in a 2U. So that's a lot of data in a very small package that also is extremely fast.
That's ten petabytes in a 2U,
Yeah. So how do you
right?
protect
Did I do my math right?
that?
Yeah,
Yeah,
that's
40.
crazy.
Yeah, 40 times 25. That's in the 10 petabyte range in a 2U. And yet those drives are also Gen 5 drives, so they're extremely fast. Each drive can be read at 14 gig a second, and you could write to them at 7 gig a second. And um, so the problem becomes, how do I protect that data? How do I do it without bottlenecking performance? And if I do lose one of those drives, how long am I running in a degraded state? How long does it take to rebuild? How resilient am I during a failure to make sure another failure doesn't take me down? And though, so the traditional technology that's been around forever needed a little bit of revamping to keep up with this, and that's where we came in.
So, do you guys see your system, the speed increase that I need? Well, we'll get more details into it, but do you see that large volume of data only being used for training these models, or are we seeing large amounts of data being used in like everyday use in the back office? That because training models is pretty data intensive, right? But
It is.
what about a normal back office, right?
Well, and there's other areas too. It's once you have a trained model, now you could be doing edge related inference, for example, where I'm capturing a huge amount of data and I want to do analytics against that real time, and I have to be able to write it quickly. That could be video, it could be radio frequency. So we get involved in a lot of military applications where they're doing that kind of edge data collection. There's no way to move it to the cloud quickly. It's a huge amount of data, but they need insights into that immediately. So they'll have trained models to do local inference, and speed is also very important in data protection.
Okay, so your solution can work out at the edge instead of a ten petabyte, two rack system. You can work in a lot smaller form factor,
Oh, yeah.
but give them the speed that they need to do. So that's pretty slick. So you guys are highly scalable in solving these problems because you're right. I want to do inference at the edge, and a great example, the F-35. We're talking every time it goes up, it's like 10 terabytes of data that's collected, or 100 terabyte, some outrageous number. And I know they were actually taking drives out of the F-35 and taking them in. That was their fastest way to get things out. But um, there's a lot of data being generated out the edge.
More and more sensors every day, and more applications. That's a very good example. We're involved in some military battlefield type applications with the U.S. Army, and in addition to everything we've talked about, security becomes extremely critical, and so you have to start looking at things like data at rest encryption, and how well is it encrypted and how well is the server protected, because sometimes things in the field could get captured or left behind, and you want to make sure that those assets don't provide any kind of actionable intelligence to the bad guys that might find that in the field in that kind of a scenario. So um, we work with a lot of different companies to create solutions like this in partnership to deliver that kind of capability, capacity, speed, performance, data protection, and encryption all in one package.
So that's interesting. So before, people would kind of cobble this stuff together, right? If I remember right from my days of when I was a CIO, we bolted encryption on at the end. It was just cobbled together. What you guys provide is kind of a more seamless system that, hey, I plug this in and I'm ready to go type of thing. Is that the idea?
Well, most what we're working with are what are known as SED drives or self-encrypting drives. So these are NVMe flash drives that have controllers on board that will encrypt
Okay.
the data as being written. What we have to do is manage the keys, help manage the life cycle of those drives, and not impede the performance as we're writing data, and also provide data protection. There's a whole other side to it as well. If I have a server that has 10 drives in it, and I pull one of those drives out and it's an Opal encrypted drive, it's virtually unhackable and it's a brick. But what if I capture that whole server and I'm actually able to turn it on and it comes up to a login screen and I hack into the OS? I have the keys to the kingdom. So
Yeah, yeah.
now we're dealing with encrypting the boot devices and then having some sort of pre-boot authentication software on the front end. And so we partner with several different companies that provide all parts of this solution, and that's what the military chose, was this design and reference architecture for the Army.
Okay, so explain a little bit. I think we understand the problem. So it's a lot of data. It needs to be protected. Um, Explain a little bit about what your guys' product does to
Sure.
help solve this problem.
So I think RAID is nothing new. RAID, the concept of RAID, being able to take a group of drives and make them appear as one large workspace, one large volume. But if I have four drives, 25% of my data spread across the four drives. Each drive has 25% of my data. If I lose one, I lose everything because I just lost a quarter of my data. So
Right.
simple RAID 1 and 0 and 10 is just a mirror where I'm you know, synchronously replicating every block that gets written. The problem with that is it's high overhead. It's also causes write latency because everything has to be written twice, and it consumes half
That
my
makes
space.
sense. And
So
you're
how do I
hitting the
protect
bus
that?
on each one
Yeah,
of those rights. Right.
yeah, and how do you protect that? So schemes using parity-based RAID were developed years ago, and they use these algorithms called Reed-Solomon to generate parity information. That parity information is striped along the drives along with the actual blocks of data. And if I lose a drive, I have the capability to go read the striped parity from the other drives and do a rebuild. So the traditional methods around that involved usually a hardware read controller. And with a hardware read controller, when these things were developed, you were dealing with spinning hard drives, which were relatively slow and have a lot of latency.
Right.
So your traditional hardware RAID controllers had cool things like battery backed, memory on board for caching, so that I could write and write really fast, but the data never really went to the disk. It's held in cache, and then it gets slowly doled out to the drives behind the scenes. But the application thinks it's written. That's why you have to protect the cache. Um, and so the problem then becomes when I plug one of those into a motherboard on a server, it's generally a PCIe slot. And if I have a card that's PCIe Gen 4 by 16, it
I
can
can
never
take
go
it out.
faster than 32 gig a second. I'm limited to 16 lanes.
Yeah.
Well, now we
Right. Got
move
it.
away from hard drives and let's talk about not even SAS and SATA flash drives. Let's talk about NVMe. An NVMe drive directly plugs into the motherboard and it needs 4 lanes. So if I have 10 drives, that's 40 lanes. Well, if I plug 10 drives into a card that only has 16 lanes, I just took 40 to 16. It's just like going through a toll booth on a highway. Everything has to slow down to get through that bottleneck, right? So that's the problem with hardware RAID. The flash drives have gotten far faster and they're very PCIe lane hungry. Um, so then the other way to do it is I just have all my drives plugged in and I run software RAID. If I run software RAID, it's now sitting on my CPU. And the CPU is not particularly good at math. That's why we have GPUs now for graphics and all this stuff. CPUs, you want to run your applications there, but if I'm running RAID infrastructure workloads at the same time I'm trying to run an application, I could have 60% of my CPUs dedicated to just protecting the drives,
To just taking,
and it doesn't
yeah, yeah,
scale.
yeah. I get it.
And so we recognized that that was only going to get worse and worse and worse because every generation of PCIe, the speed of the drives is doubling. So Gen 6, we're seeing Gen 6 drives right now testing at 28 gig a second, which means it would only take one of those drives to overrun a Gen 4 by 16 hardware RAID controller. So how do you solve the problem? And what our team came up with was a two-pronged approach. First, we wrote our own software RAID stack, and we accelerate the performance of the RAID by executing all of that code on an NVIDIA GPU. So we use an off-the-shelf NVIDIA GPU. We have a CUDA-based driver, and it sits there. So your CPU is now not busy anymore because it's happening on the GPU. The GPU is really, really fast and really, really good at math. Excuse me. So the second part of this is how do I get out of the data path so I don't have to read everything into that GPU and write it back out of that GPU? I would be back to the
Right. Yeah.
same
Yeah. Because that
416 lane limitation. And so since everything on PCE is a peer of each other, the CPU, the memory, the drives, our cards, everything you put in, we created our own patented peer-to-peer DMA technology that allows us to act more as a traffic cop. So when we get a read, what we do is we go to the drives where the data is, and we tell those drives, send your data straight across the motherboard to the application. We don't have to read it in and then forward it. That would add latency and a hop into the data path. So the two things we do is we got out of the data path with a patented peer-to-peer DMA technology, and we accelerate the parity calculation by using a GPU, which frees up your CPU. And so that's kind of the magic that we've created. And we have a number of different models that we support in the market, and so we got some exciting new things coming out too.
So that's really interesting. I mean, the way that you described it, that you're out of the data path. You're just calculating the parity in the GPUs, which makes a lot of sense, right? I mean, use it for what it's there for, and freeing up the CPU. Um, Typically, these machines that you have are these typically dedicated to do to just do the storage, like I have a storage server, or can I run other workloads on it, like out at the edge, right? I may not have the power and weight to just have one storage node and two compute nodes.
So you just kind of described our new product coming out. Um, we use very inexpensive GPUs that have just enough horsepower to handle 32 drives and not a lot of headroom to run an application on that GPU, but it makes our solution inexpensive. So if you were just going to build a storage server, that's an ideal solution. Um, the problem comes in, what if I have an 8-way, Hopper or Blackwell GPU server, and I've got 16 NVMe drives in that thing? How do I protect those? And if I don't have slots, I can't necessarily go buy another GPU to run Graid Supreme RAID on. So we have a new version of our
Right.
product called Supreme RAID AE, which means AI Edition, and it's designed to run on whatever GPU you happen to have. And so if we go sit on a Hopper or a Blackwell or an A100 or one of those enterprise, very high end, very expensive GPUs, we the resources we use on that to get the same performance we get on a little bitty cheap GPU is very tiny. So we only use a very small percentage of the resources of
So
something
I
like an
can now take
H100.
advantage. Yeah, I can now take advantage of a beefier GPU, or maybe I'm running on even a smaller form factor, right? Maybe a micro data center in the back of a Humvee, um, right, where I don't have a lot of power,
Hmm.
right? I can still run this on a lower power GPU, but still get some work done, right,
Right,
on the CPUs. That's what
right,
I'm hearing. Is that right?
right. And you mentioned the F-35. There are applications out there where there are ruggedized servers being put onto these aircraft, and they've got GPUs on them. And there are advantages to running our software on the GPU, not just for performance reasons, but power and heat is incredibly important. And if we can free up the CPU enough, it's possible that the customer could use a lower cost CPU that generates less heat and requires less power, because they don't need that much to do the workload that they're doing. So it's a right sizing your hardware for the application. But with this new AE version, customers who already have a GPU just need to buy software from us, and then you could run our software on that GPU. And we've added GPU direct storage and some other NVIDIA features that also improve the performance of getting the data from the drives into the GPUs for training and things. And so that's really exciting that we have this, and we don't force you to buy any hardware anymore. And you can run your application on that
That
GPU with our software because it's a shared model.
no, that's pretty clever. So where do you see the future of this going? I mean, I love the idea. Where do you see the future going in the data management space? I can't even talk. Specifically, what AI is going to drive in this space. Do you see anything new or exciting happening?
Yeah, in fact, we're an NVIDIA Inception startup partner. There's 23,000 companies writing software, CUDA-based applications, if you will, for NVIDIA GPU platforms using their frameworks. And um, we were one of 60 out of 23,000 that were invited to have a kiosk at GTC in the Inception Pavilion. So it was, we were very flattered. It was very exciting to be there. And one of the things that I noticed when I saw Jensen speak at the keynote is he's talking about how fast GPUs are increasing in performance. So Moore's law used to be every 18 months. If everybody remembers Moore's law, CPUs would double in performance every 18 months. GPUs are on a 12-month cycle. So it's even faster now. There is an inflection point coming where storage will not be able to feed the GPUs that are coming as fast as they need data. So why would I go buy a $50,000 GPU and yet I can only get
Yeah.
30% utilization out of it? I might as well buy cheaper ones and get them 100% utilized. So NVIDIA has recognized that that is a future issue where we need to work together with multiple disciplines within flash, within controllers, within storage array technologies, within RAID protection, to help accelerate the data performance even more. And so they actually have an initiative called Storage Next, and we're a part of that initiative with a number of other companies, and it's publicly announced and it's out there. So the idea is, how do we get to the point where it's not about cost per gigabyte anymore? It now becomes cost per token, because when we start talking agentic AI, you're generating tokens, and so it becomes a different kind of thing where you're not talking about streaming huge, large data files, but you're creating millions and millions and millions and billions of tokens very, very fast. So it kind of twists storage around a little bit, because storage is really good at storing big chunks when you think about a video file. But
Yeah.
when you talk about
Tokens are very
tokens, which
big.
are little tiny things, you have to change the way storage works to get that fine grain access. But what we're looking to achieve is somewhere close to 100 million IOs per second to one GPU off of storage. And so it's going to take a number of companies a number of years to develop.
Well, I mean, there's been this concept. I mean, Intel developed their Optane memory, which was non-persistent or
Mm,
persistent non-volatile memory.
right.
Great concept, because it blew up some tiers of storage. Do you see us moving to something more like that, where I start getting rid of some of these tiers of storage and I just have non-volatile memory sitting there that I can just tap into direct? I mean, why not?
I think in 3D Crosspoint and Optane was very cool technology, but it kind of got squeezed because DRAM got cheaper and Flash got faster. So it got to the point
Right.
where it just didn't make sense. Um, there were some applications where persistency was good to have it act as PMEM, right? But what we're now seeing more of are things like being able to create storage or memory, shared memory pools using DRAM and using CXL
And CLS.
fabrics to be able to allocate
CLS.
memory to a server as the workload demands. And when that workload is not on that server anymore, pull it back out. So now I don't have a big, empty, expensive box with a lot of memory in it that's underutilized. I can keep that memory utilized by putting it where the workload needs to be. And so you'll
Right.
see this kind of thing. We call it disaggregation as well. Within the space we're in, the disaggregation is happening where we're going to focus on delivering NVMe across a fabric to a device. So instead of having everything captive in that server, you would have an array like
And now it can be anywhere that it's
server
connected.
serving up volumes to across a fabric. And now I can kind of spin up a server on the fly that's got the right mix of memory, GPU, CPU, and storage in it. And when that workload's done, I can tear it down and rebuild a different server, all using software.
So true software defined infrastructure.
It's interesting. There are a number of companies out there that we partner with, and I used to work for one called Liquid, and there are others out there. I think Serio and Giga.io, and now you've got the CXL companies that are building these fabrics, and the Gen Z and CXL merged, which helped simplify that world. And so I just came back from Dell Technology World, and I saw some CXL demos that looked very interesting there.
Yeah, so it could be interesting as we see the market drive, and maybe Gen AI will be the driver that makes this happen, kind of blowing up the traditional von Neumann compute model, which I would really love to see blown up because if you look at, there's a lot of speed that can be gained by not having to constantly marshal data structures
Yes,
like we have to do today, right? I mean, a simple thing from taking a memory data structure to putting it on a drive in a file system or even in a database, we're talking 20 cycles minimum.
yes.
And if you can get rid of that, that increases my speed by 20x.
Well,
That's a
yeah,
huge change in the way we think about compute.
and when you think about workflows, data has gravity, and if I have to copy data from one stage of a workflow to another, then I'm wasting time moving something. Instead of moving the data, why don't I move the drives virtually as a mount point so that maybe I do ingest on one server because it's got a lot of high performance NICs on it to handle ingest. But now that I've got my data, I want to do tagging and training and those kinds of things
I want to
that
do a lot.
maybe
Yeah.
require a higher powered GPU for that part. And then at the end, that data needs to be made available to an inference machine that doesn't quite have as big of a GPU in it because now we're just at
Well, you don't need a GPU at all to do inference.
potential. Yeah.
That's the big
So
lie that Jensen talks about all the time, right? Oh no, we're the only company that can do AI. Total lie. Most of the inference done in the world is done on Xeon processors,
yeah,
um, and so there's still a lot of relevance out there. Um, I have an issue with Jensen. I want him to come on the show so I can go toe to toe with him on that
that would
because
be cool.
um, yeah, that would be cool. Well, because the truth is there's a lot that could be done on current infrastructure out there today, and especially with these new data architectures that you guys are talking about. I can do an impedance match with the speed of my drives and my CPUs, and at a much lower cost, lower power, highly sustainable. I can get some solutions out there that work today. So, hey, Kelley, this has been a great conversation. For my listeners, I know they're going to love how deep we got in technically on how raids work and all that. That's really cool. You guys, if they want to find out more about your solution, where do they go to find out more?
So our website's the obvious first choice, graidtech.com, GRAID, which is kind of an acronym around GPU based RAID. And it is Graid
Love it.
technology, not G-RAID. And we get that sometimes. And our product is actually called Supreme RAID. So um, that's the first place to go. We've got lots of resources there. We also have many, many partners in the market. So um, companies like I mentioned, Dell, Supermicro, Gigabyte, Giga, we have many, many partners out there that we work with in this ecosystem. And I'm also working with a number of partners specifically that we work with in the ruggedized military space for some of the applications we had discussed earlier. And so they're a good source of information.
Great. Kelley, thanks again for coming on the show.
No problem. Thanks for the opportunity, Darren.
Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and embrace the digital revolution.